Thanks, everybody. If you're not familiar with EWI, we're Edison Welding Institute is what we were typically known as before, but we've shortened it to EWI. We do contract research and development for companies to help them bring technology into their facility to help with just moving things with the new paces, automation, pretty much anything that has to do with welding. So the talk today is on friction stir welds. So I'll go over what friction stir welding is if you're not familiar with that. The defects in friction stir welds. There's a lot of different defects in those welds compared to other welding technologies. And then how do we inspect friction stir welds? So the challenge that I'm going to share with you today is something that tests we've been performing on a friction stir weld configuration for quite some time, but the geometry of the weld, or the part that we were joining together, changed significantly enough that we can no longer use the typical setup that we were using with phased array UT. So we needed to figure out a different way to be able to scan the whole weld. So we use CIVA to help us do simulation, look at the different algorithms for UT to reconstruct the scan, to try and find all the defects. Then we use those parameters that we have in CIVA, put them into our inspection tool, and run the scans, reconstruct the data, and then I load the data back into CIVA and do analysis in there so we can do a little bit more in-depth review of the data. On the picture here, this is our larger friction stir machine at EWI, so all the welds were built on that machine. So you can see with the person standing there, this can take some pretty big panels. So that's what these welds were very long panels of welds. So friction stir welding is a solid state joining process. There should not be melting typically. We usually use it to join aluminum and titanium and copper. Those are probably the big ones, and then magnesium, steel, nickel. Dissimilar metals can also be joined. It consists of this pin that drops into the material. It's stopped by a shoulder on that tool so that the pin drops into the metal once it heats up enough, and the whole tool rotates, stirring the metal together. So if this was a butt joint here, then we're stirring the metal from both sides and we're running the tool along the length of that weld. The tool pin has these flats and threads on it that helps mix the material together. So we have to make sure wear on that tool is uniform. It should be a non-consumable tool, so this material is changed depending on what material we're welding. The friction stir weld, the resulting weld, the friction stir welding is a frictional process. So like ultrasonic welding, if you're familiar with that. So the frictional heating and dynamic recrystallization are what makes it solid state, and we end up with a very fine microstructure in the weld. And this is what the weld looks like when it's all done. The cross-section up here matches the picture down here, so you can kind of see the different weld regions. In the weld itself, we have the stir zone and then the flow arm where that material was grabbed and mixed together. So you can see the different colors up here. Then we have a thermomechanically affected zone, this dark part, and then our heat affected zone. So you can imagine that we could have defects at any of those different areas in the weld that we need to target. We can have significant lack of fusion if we can't get through the entire thickness of the metal. And we do have very little deformation at the weld surface though, so that is helpful typically. You can see some flash up here. We'll grind that off a lot of times if we're inspecting from that side. So the thicknesses for welding: aluminum, we can weld the thickest at about 4 inches. Stainless steel and titanium are a little bit more difficult, so up to about 1 inch. And then copper and magnesium, somewhere in the middle. Dissimilar alloys are also possible, and here's just some cross sections of what those types of welds look like, or those materials will look like once they're welded together. Now the defects for friction stir welds can be numerous and depend on the settings that you use in your welding process. So on the x-axis is rotation per minute, so that's the rotation of the tool itself. And the y-axis is inches per minute, is our travel speed along the length of the weld. So if we go too fast with our RPM, we can get things like defects at the fan surface, where those two pieces of material that are butt welding together are not fully combined. If we run too fast on the pin and we're scanning too fast along the weld line, then we start to develop a lack of penetration situation. If we're going slow with our RPM and we run along the weld too fast, then we have a cold weld and we get something like scalloping or wormholing, where we get voids all along the edge of the weld pin to the base metal. So all of those things happen pretty easily, but we do have a process window that the welders are targeting. So with NDE, we can help them narrow in on that process window rather than doing cross-section and cross-section. Normally, we use phased array UT to inspect the friction stir welds. We can inspect them from the top of the weld or the back side of the weld. We will use 0 degree beams, or we'll offset them with an angle beam and look from either side of the weld. So in this scan, you can see the stir scallops here on the surface pretty easily. This is where the pin is retracted from the weld. It leaves a hole behind usually, and then they'll fill that in. So that's another area of concern. Sometimes that just gets chopped off though. So with phased array UT, 0 degree wedge, we can see the whole weld. We can see the back surface in the B scan here, the top surface. We get a pretty good idea of what's in between along the weld surface. We'll look at the sector scan, look for features that don't belong in the sector scan all along the B scan. If we were using angle beam, we would offset this from the weld and run the angle beam from either each side of the weld in pulse echo, or we would do pitch catch and bounce back and forth across the weld to make sure we cover the entire thickness. So this was our challenge, was this ribbed plate. And there's a butt joint in here. The weld actually happens in between these ribs. So the pin comes down, plunges, and welds here, and then we run the tool all along the length of that plate. What happened was these ribs geometry became really narrow. So now we're looking at 2-inch separation of those ribs. And normally we inspect from the back side here, while the tool is down here, just because getting the probe in between those ribs is tricky. You have to grind off the material if you're going to do 0 degree inspection. So we measure from the back side. But now, if we put our angle beam probe on either side of the weld, we have these ribs to contend with, and all of our sound just bounces right into those ribs. So that's a problem. So we have to go right on top of the weld, which is fine for 0 degree or for some angles in our wedge or in our angle beam. But it does make it challenging, especially if there's lack of fusion in the weld, because that's harder to do with phased array going right on top of that lack of fusion. So we created a calibration block, And initially, this was supposed to be just quick and dirty and just find some defects if they're in there, right? But we need a calibration block if we're gonna actually identify them. So we finally made a calibration block. We put in some side drilled holes, and we put in some surface notches on the back side and the top side so that we could catch lack of fusion, or we could catch defects that were from the stir. Then the plan was we were still at this point using phased array to do the inspection. So we were modeling the phased array, testing that out on the weld, and then reconstructing the data to see if we could find lack of fusion. And we tested this with a 0-degree wedge, a 30-millimeter thick wedge, and a 33.7 degree wedge here. We just used a 5 megahertz 60 element probe. Initially, we were just using phased array software, but then what I'm going to share today is the improved results using TFM. So this used the TPAC Explorer, the 64128, so we could use all the elements in the probe. Prelude 5, and then we have CIVA 2023 that we did the simulation and reconstruction in. And with the CIVA software, you can load your data files in from several different data collection systems. TPAC has a few in here. Prelude is the one that I would use if I was using just phased array. And then the TFM imaging is the one that I'll show our reconstruction in today. That loads in the TFM data from Prelude. So simulation with CIVA, if you're not familiar with it, we can tell it what equipment we're using. We can put in the elements that we want to use in the probe. We can limit it. We can group them together, just like for phased array. We want to group certain elements together to do an inspection, steer the beam. That's what we did initially with PAUT. So we're in this situation, because I was trying to target that lack of fusion, we put in the 33.7 degree wedge. We have to put the whole probe over top of the weld in order to not get all of our sound to go into those ribs. You can see the defects here, these little red circles. This one's kind of hard to see, but those were my simulated side drilled holes. I just wanted to bounce off of those and make sure I had everything going the right direction. I wasn't losing any of the group that I selected to the ribs, to bouncing off of the corners and becoming useless for us. So that's where we started. Then we switched to TFM. The same wedge, same probe, but now we're using, we have the ability to use the entire array of elements. And for the TFM, we select a window that we want to do the reconstruction in. So we're limiting the area that we're looking at. And from there, you can kind of see the bright spots where my artificial defect is. Those are lighting up really nicely. They're not distorted. We don't have a lot of scattering off of those defects like we did at PAUT. And we're catching both of them with our 33.7 degree wedge without using the higher angles because we're shooting at all elements are firing. So we can catch these defects in direct measurement if we need to. So the simulated data after running the TFM, we can take those side drilled holes. I can check to make sure that the probe setup that I have was setting the depth of those holes correctly, measuring the width of them correctly. So all the parameters that I have, those are good. I can take the parameters that I put into CIVA and plug them into my data acquisition system. Before we go to that part, I'm sorry I'm jumping around, but for phased array, when we look at this weld with lack of fusion, with PAUT, there's a significant amount of noise that you can see up here. This is just surface noise from the probe. This was at 0 degrees, 30 millimeter wedge. You can see some distortion here from the notches that I put in the calibration block, but you can also see this is measuring at 3 millimeter depth or so for this hole right, or this notch here. So we're actually, that notch is somewhere up in this noise. So we can't resolve that notch. We don't know actually how deep it is. That notch is only something like 0.5 millimeter deep. So we've lost a lot of information up here. And then we continue to lose information on the back wall because we also put notches in the back wall to try and catch in the stir zone. So you can see some shadowing here from the notches, but otherwise they're lost. And we also have reflections from the surface notches because in the phased array it's flipping those images upside down. So now we've got a lot of information that's just buried in the noise that's just typical of our scan. So that's why we need to try TFM. And with our TFM setup, we also use the 0 degree setup, but we did angle beam as well because in our simulation, it showed that we were able to pick everything up. Both of those probe configurations need to be directly over the weld because of our ribs in our part. We used the TFM in pulse echo mode, and then we reconstructed, FMC in pulse echo mode, and then we reconstructed using delay and sum phase coherence imaging. So the PCI was new to us, but that cleaned up our signals really well. We did not do any TCG this time, so keep that in mind when you're looking at the scans. There's no gain control with the depth of the defects. And all the elements in the probe are active. So we didn't take any of the elements out. So this is now the scan of the side drilled holes on that part. Here's the calibration block. You can see the flash from where our stir tool plunged into the side. So it leaves these little flash wings. Our 0 degree wedge and probe right over the weld. I can see the flash in our scan, so I use that to center the probe, which makes it really nice. And in our TFM image, you can see the side drilled holes. The gain's turned up high for right now, just so we can see it, but the 2 side drilled holes, this is just a reflection of the deeper hole here, the 20 millimeter hole, and then our flash, of course. So this is the noise that we get from the surface now. It's much improved. The TFM also lets us isolate a little more of the back surface, which I'll show when we turn the gain down in CIVA. So we took this data, we ran the probe along the length of the weld, and saved everything, loaded into CIVA. In CIVA, I can chop off the back wall, moving the gate around. I can add my own gates. I don't have to save gates from the original software. I can make new gates. So this gate, I took away the back wall so I could just see the surface notches on the part. And with the gain not turned up artificially, you can see some shadowing here on the lighter, shallower notch, but then otherwise they come in pretty good. This is this one side drilled hole over here, and this is our double side drilled hole on the left. If I look at the whole scan of the plate with the back wall in, the C-scan, you can see the notches on the back side coming in down at the bottom. So those are not buried quite as much as they were with our regular phased array. And then our surface notches in the B-scan, you can pick those up pretty nice. We can measure the length of those. And our side drilled holes coming in. What I thought was interesting was without TCG, the gain was fairly consistent enough that it seemed pretty reliable to measure those defects. And then the T-scan up here, this is a slice through the C-scan. So this vertical line here, if we were looking in this direction against that vertical line, that's what we would see at that selection in that scan. And the same thing for the B scan over here. There's a vertical line. You can't really see it, but that corresponds to the same line over here, creating this, T scan, and then the corresponding A scan for this blue line. So the blue line here is the A scan pixel that's over on the right. The T scan, I also have it focused on one of the side drill hole, surface notches here. So this is the surface notch, looking at it from the narrowest region. So we can get an idea of how wide that surface notch is, or that lack of fusion. And then looking a little bit closer at those surface notches, we can also tell that they are at different depths. Those different depths have more amplitude as we're getting more of that energy down into that notch. So we have some more higher amplitude here. And then this is what the top of the plate looks like, those notches. So the yellow circled notch is our shallowest notch, which is about 1.6% of the thickness, and then up to 2.2% of the thickness, which this one's about a little more than 0.5 millimeter, and this is a little less than 0.5 millimeter. And then the top view of those notches, I also put them over here so you could see how they line up with the length of the notches in the image. And again, the T-scan with the notches, just a closer view so you can see the T-scan. This is from the short direction of the notch, I guess. So we're looking at the width, the narrow width of the notch. We're also picking up the notch that's on the stir side of the weld down here. And then again, our flash. So we can use the flash to line everything up. The next thing we did was create artificial defects in some plates to test this out. And we did a wormhole test. So we ran the tool rotational speed slow and drove the pin along the length of the weld too fast, created the wormhole. And after collecting the scan data with the TFM, we reconstructed it, and you can see the wormhole along the length of the weld. This is the whole length of that plate, and then we can see the wormhole showing up here as it comes in and out of focus on the plate. I also took the back wall away, so we don't have interference with the back wall. We're just focused in on the area between the top and back surface. So we're getting a really good signal from that wormhole. And here it is on the T-scan. So we can get an idea of the diameter of that wormhole. We're not scattering too much off of that. So that's what we can track along the length of the weld. And then next we did a lack of fusion. So this was running the tool too fast along the length of the weld and rotating too fast, so we weren't completely mixing the full depth of the material. So here's the lack of fusion depth, and then you can see the lack of fusion at the base. There's some hooking, so there was a little bit of mixing down here, but it didn't fully mix. And running the data in CIVA again, I took out the back wall so we could focus more on the top surface and turn the gain up a little bit. And we can see the line from the lack of fusion running down the length of the weld. We get this nice dark blue region around that, so we know that there's something else along the middle of the weld that doesn't belong there. So that was reassurance that we were picking up the lack of fusion compared to the phased array, where we couldn't resolve that before, even when taking out the back wall, because of all the surface noise from the phased array. So finally, We ran this with angle beam just to make sure we were catching the features accurately, see what it did. Even though 0 degree seemed to do okay, can we pick up the lack of fusion a little bit better? I turned the gain up really high here just so that you could see the profile of what this angle beam scan looks like. So I've got the probe directly over the calibration block, but we can't see the entire weld. If we move the probe back, then we lose more of our beam to the ribs. So we have to scan this from both sides, which is not unusual. So we just scan it from one side, flip it over, scan it again so that we catch each of these corners. In the Prelude software, you can draw in your weld geometry. So I put my weld geometry in so that I could track my flash and use that as my guide. And then I could make sure that I was aligned properly all the way down the length of the weld. So here's my flash on this corner, here's my side drilled hole, and I can run along the whole length looking for defects in the weld. You can see at the top here, using that at the higher angles, we're not really picking anything up on the surface in this shot, which is good. So we're not getting a lot of surface noise. When we look at the data, reconstruct the data, and look at it in CIVA, with the angle beam transducer, I thought it was interesting that we probably need to use TCG now. So with the angle beam probe, our gain, we're very saturated with the features on the bottom part of the plate. And on the top of the plate, you can see our surface notches aren't coming in very good, but we can still see them. And I've got the gain really turned up quite a bit to pull in these surface features. You can see how I'm saturated here. And we still don't have surface noise interfering with those notches. So I'm confident that we can still look at lack of fusion with this configuration with a little more work with gain distribution there. So here's just this is the notch on the back side coming in. And you can see now how it's kind of angled instead of circular that we had with the straight beam. So different ways of scanning the part still gave us results that we were looking for, but without setting our gain using the angle beam, we could miss some of those surface features. So something to keep in mind for us. So, so finally, using TFM allowed us to look at these new geometry configurations, scan the entire weld, pick up the lack of fusion that we weren't able to see with phased array. We also simplified the inspection process using TFM. We didn't have to worry about grouping elements because we're firing each element one at a time and then listening to the reflection with every element. We didn't have to do any finishing to the material, grinding or anything like that. So that worked out really well. The straight beam inspection gave us the best coverage, and we were still able to see all of the linear flaws. And I didn't show the other algorithms, but the DAS PCI, that's the TFM reconstruction with the phase coherence imaging, gave us the best images of the top and back surface. I did use the planar wave imaging, which is a faster reconstruction method, but it was still too noisy to, we could see everything, but I didn't like it as much for this application. And no TCG being used with our 0 degree inspection was still gave us good consistent results. So that's it. If you have any questions, I'd be happy to answer.
Okay.